Good morning. Happy Wednesday. Very important.
Okay.
It'll just be a video. Okay. And so after class on Friday, I'll post the video so you can watch it whenever you want, obviously. But you'll have to watch it before class next Friday, because then we're going to review it all. Okay. And then that's going to be on your test. So that's very important. Test number 2 is on April 2nd.
Is the video going to be as long as this class?
Yes.
Okay.
It's an hour and 52 minutes. I just checked. So I guess I went over by 2 minutes. Rude. But I know you guys are watching it at like double time, so I don't feel bad. It is from the old version, so I made videos to match the old version. So it's going to say chapter 5, but it is chapter 7 now. They just rearranged the chapters. And the reason I'm not posting it until after class on Friday is because we need to do 7.1 to introduce the t distribution and things like that. And then we'll be able to branch out into 7.2 and 7.3, which I smushed together. Okay. And then we'll review it next Friday. Okay. And so don't show up Wednesday next week. Okay. I did put it on Moodle too on the day, but just there. Now I've said it. Last day, we talked about the chi-squared distribution, right? And so the chi-squared distribution tends to look something like this, right? Chi-squared, chi is a Greek letter. Okay. And the chi-squared distribution starts at 0 and moves out this way. Okay. So it tends to be smushed, smushed or skewed to the right. Okay. But the shape depends on the degrees of freedom. Okay. And so, for example, if you only have 2 degrees of freedom versus maybe 5 degrees of freedom, right, the shape is going to depend on those degrees of freedom. And on your formula sheet, it says how to calculate your degrees of freedom. Right? Last day we talked about, okay, the chi-squared goodness of fit testing, right? We have some idea about the distribution that we're expecting to see, right? And then how does that compare to what we observed, right? And then I give you the degrees of freedom. Now the chi-squared test for independence is what we're going to introduce today and talk about today. Just like we saw in the Z distribution, we can calculate the same test statistic in a couple of different ways, but then once we have that test statistic, right, either Z or chi-squared, then it behaves the same. Okay? Now the chi-squared test for independence, the null hypothesis, and remember for chi-squareds, it's nice because we only do hypothesis testing, right? There are no confidence intervals because it's not symmetric anymore, so it doesn't make sense to build an interval, but we do hypothesis testing. Now the null hypothesis is that the variables are independent, which implies we have 2 categorical variables. We've seen that before, right? We've seen that kind of 2 categorical variables. What did I have on the test? Now I can't remember, but we can say maybe male, female customers, and maybe they drink their coffee black or with sugar or with cream or sugar and cream. no milk around. That's too many categories. So two categorical variables looks like this. It generates a contingency table. And so we'll be in a contingency table, which we've done work with already, right? Back in chapter, I don't know what, chapter 2, 3. We'll be in a contingency table. Right. We have a variable here, but we also have a variable here, right? So we have a gender variable. So a gender variable. And here we have a coffee variable, or I guess coffee or tea or whatever. Who cares? And both of those are categorical variables. So now I have a two-way table or a contingency table, right? Contingency table slash two-way table of two categorical variables. Now, from what we've seen before, right, we generate counts in each of these cells. And then we were able to find conditional probabilities and things like that. But now what we're interested in is the independence. Okay? So is this gender variable, is it independent of the coffee variable or vice versa, right? Does how people take their coffee depend on their gender, right? If it doesn't, right, then they're independent, and we would expect similar counts for black coffee for both genders, similar counts for the sugar, right, kind of hovering in the same range, right, cream, sugar and cream, right, and then, but not necessarily the same across one gender. Right. And so that's what we're going to analyze today. If we only looked at, so if we ignored, I'll just scratch this out temporarily. If we ignored this, then I'd be down to one variable, right? And maybe, right, if I was interested in this distribution, is it even, right? An even distribution, then we're back to a goodness of fit test, right? Or maybe I have some hypothesis about the distribution that I'm expecting to see, right? And then you want to compare that distribution, right? So if it's just one variable with more than two categories, right, 3 or more, then it's a goodness of fit test. But if you have a two-way table like this, it's going to be a test of independence. Okay. And so that's your biggest clue. Okay.
Wait, sorry, you said if you have 3 or more, it's a what?
It's a goodness of fit test like we did last day, right? And because if you only have two categories, let's say just you either take your take your coffee black or not, right? Then you only have two categories, but then you could boil it down to a one sample proportion, right, of black over the total, right? Black coffee over the total. Or even if you wanted to compare it across the genders, if you boiled it down to if they take their coffee black or not, right? Then it would be two sample proportions, right? And then if you only care about, right, the distribution, right? But now I have 1, 2, 3, 4 categories, right? Then I want to compare it to some hypothesized distribution. Okay. And now we've built it up to, okay, now I have two categorical variables. And I want to know if these two, if the gender, right, helps me determine what the distribution of how they take their coffee is, right? Otherwise, if not, then we consider them independent. Nice. So if we jump ahead a little bit, our chi-squared is going to be calculated the same way as before. It's the observed minus the expected, and then we square it, and then we divide by the expected count, and then we add those all up. It's just how we find the expected count is a little bit more elaborate, but also, in my opinion, a little bit easier than the goodness of fit test, because it's just going to be the row total times the column total divided by the overall total for each of those cells. And we'll look at an example, because if I have to make up numbers, it'll take me forever. And then the degrees of freedom, how we calculate it, it has to take into account the number of rows. So we take the number of rows minus 1 times the number of columns minus 1. Right? We need to know how many categories are we handling here. Right? And so the number of rows minus 1 times the number of columns minus 1. Nice. But once we have the chi-squared and its degrees of freedom, then we're back to where we were last week. You had me worried. No. Then we're back to where we were last week. And we can use our mini table. Of course, if you Google it, you can get a bigger table of chi-squared values, but I feel like that's too much. And I don't want to bring a bunch of more paper. So that's why I put it on the formula sheet. So it's just tiny, just tiny. Okay. So we'll do an example. Let's see here. I don't have Candy today, but I do have a Candy example to build off of the one that we built last day. But maybe what I should do is just outline those different examples of the different types of questions, like we said, because I said them, but maybe it's nice to have kind of a framework where we use these two variables. So examples of the different types of questions we could ask using the gender and coffee variable, which I just made up, variables above. One sample proportion we'll start one sample proportion type of question could be something like, do more than 50% of people take their coffee black? Or let's say, does a majority, right? The one sample proportion, they love using the majority, which implies more than 50%. Right? And so, is there evidence? Whenever you see, is there evidence, that's going to be a hypothesis test. We're not going to do it, but I just want to show you what it would read like. Is there evidence that a majority of people take their coffee black? In terms of our counts, we would have, they take their coffee black or not black. And then over the total, right, the total count, let's say 34, 27, right, which means that, what's 34 plus 27? Math. Math is hard. That's his total, but I drew a line over it. You are not doing it wrong. Nice. Clean this up though. And maybe I should do this count instead, call it a count. Because we can zip this up, right? We could have zipped up this table, right? And said, well, I'm gonna have some total count down here. So then if I ignore the gender for a little bit, then I can look at the total count of those who take their coffee black and lump up all the other ones. And that would make it a one sample proportion type of question. And your null hypothesis would be, is P equal to 0.5? And your alternative would be, is P greater than 0.5? Right, your hypothesis is always about the population proportion, but your sample proportion here would be 34 out of 61. And then from there, you're ready to go through and do your hypothesis test, but I'll leave you hanging there. Because what does a two sample proportion look like? A two sample proportion type of question could incorporate the gender. And there's a couple that we could think about, but these are probably the most straightforward. Is there evidence of a difference in the proportion of males and females? I know, outdated, but I'm a one-trick pony. Males and females who drink their coffee black. Now, you would still have your black and not black, right? Zip all those up. I was gonna say male and gender. I guess we could simplify and say female and not female. Ah. Even using the same fake data that I had, right? If we do 34 and 27, that was from the totals right here. Then let's say I have $15 males and 19 females. And let's say I have 27, let's say, 17 and 10. I'm just making these numbers up, obviously. Now we're going to have a total of males if we want, and a total of the females. And so we could have 15 plus 17, which is 32. And 19 plus 10, 29 females. Is there evidence of a difference in the proportion of males and females who drink their coffee black? Okay, and so out of the males, what proportion drinks their coffee black? And out of the females, what proportion drinks their coffee black? Right? And so here, your P hat M is 15 over 32, and your P hat female would be 19 over 29. Those would be your sample proportions now, because you want to compare those two groups, right? And the success is the same for both of these. Huh? What's your null hypothesis? Your null hypothesis is that PM minus PF is 0, because that's always your null hypothesis for a two sample proportion question. And you have to make it question specific with the subscripts, right? Especially because if I want to know, not if there's a difference, but if significantly more females take their coffee black, for example, then I would need to reflect that in my alternative. Now, in this case, we just want to know if there's a difference. Minus PF is not equal to 0. Or if you prefer, you could write your null hypothesis as PM is equal to PF, just by adding one of the proportions, probably the last one, to the other side, right? It's easier to see that you're comparing the two this way, but this is how we find our point estimate, right? PM hat minus PF hat. And so that's why I prefer this way, but I understand if you prefer this way, and it doesn't matter to me. Oops. Which way you use. I'll know what you mean, and that's fine. But I tend to use this version, unless it's old solutions, then I was using this, kind of graduated. And I like to spice things up. Yeah. And so, right, we have some successes and failures for two groups. Okay. So now, what's a chi-squared goodness of fit test? A chi-squared goodness of fit test for this data, right? Chi-squared goodness of fit means I need 3 or more categories, right? And so we might say something like, is there evidence the distribution of how people take their coffee is evenly distributed? So then, in my mind, I can kind of unzip. What did I have? Black with sugar, with cream, and sugar and cream. Those are all different. And my counts, maybe I had 34. Oh, I guess I need to split this 27. Okay, I'll do it in a nice way. 7, 10, and 10. Kind of cheating, but kind of not. Does this look like an even distribution? Not really, right? And that's probably why we want to analyze it, but also I just made these things up. And so here I've got my counts. And so your null hypothesis would be the distribution of how people take their coffee is evenly distributed, right? Meaning I would expect to see the same number in each in each cell, right? So I take my 34 plus 27, so 61, and I split it evenly amongst the 4, right? 61 divided by 4. I couldn't have made it any worse. We need our expected counts. If it's even, I expect, it's not too bad actually. I expect 15.25 in each cell. And my null hypothesis is that the distribution of how people take their coffee is evenly distributed. And then I'm going to cheat and just copy this, because even though for the chi-squared, so kind of what we know about p-values, right? One-sided, two-sided tests, for the chi-squared, right? Our distribution looks like this. And so our p-value is always going to be just the area in one of the tails. Okay? But our alternative is always just the negation of the null hypothesis, right? We have to assume it follows whatever distribution we've hypothesized about, and the distribution of how people take their coffee is not evenly distributed, right? So that's the difference between the chi-squared and the Z hypotheses, is that, okay, even though we only get the p-value from one of the tails, we negate the alternative hypothesis. And then we're back to our chi-squared test of independence. Which we started with, right? And so now I have, it's not very beautiful, but copy. Oops. Email. Copy. We already picked some counts, 15 and 19. Could do the same for the sugar. Let's do 4 and 3, and then I'm lazy, we'll do 5 and 5 and 5 and 5. Something like that. I didn't do a question. Is there evidence that how people take their coffee, or how a person takes their coffee, and I'm trying to keep it on this one page, but you know what? No, let's go for it. Live a little. Is there evidence that how a person takes their coffee depends on their gender? Your null hypothesis has to be no, it doesn't depend on the gender until we have proof otherwise. So then we would say gender and how a person takes their coffee are independent of each other. And again, the alternative is just going to be that they are not independent of each other, just like before for the chi-squared. So for my alternative, gender and how a person takes their coffee are not independent of each other. Okay. Let's do this one, start to finish. Step 1, state the hypotheses. We already did that. I know, I'm hooked on this example, I guess. Let's just do it. So now, what are we comparing? If they're independent of each other, right? Then we're comparing, okay, within this group of people who take their coffee black, then I'm comparing these counts, right? And then within this group of people who take it with sugar, I'm comparing 4 and 3, 5 and 5, 5 and 5. Now, one of the conditions is that I need at least 5 expected counts in each cell, and I might have really bungled it. We'll see. We need the expected counts. So in step 2, we do the test. I call it do the test, but it's really calculate the test statistic. Which I have to point out now because for some reason last term, you know how on some of those assignment questions, it says, what's the test statistic? I was getting a lot of questions. What do you mean the test statistic? I don't know what that is. So now okay, calculate the test statistic. Okay. So the test statistic for a chi-squared test of independence, right, is, okay, a chi-squared in general is the sum of the observed minus the expected squared over the expected. Clean up the square. Which means I need so I have my observed counts, but now I need my expected counts. And for a two-way table, oops. For a two-way table, we calculate the expected counts like this. So for each cell, and how does it say, how does it read on the formula sheet? For each cell, the EIJ, the ith row and the jth column, that's all it's saying, is the row total for that cell times the column total for that cell divided by the grand total. So EIJ, which just means row I, column J. Oops, I should write it out. Column J is the row total times the column total divided by the grand total. So there are a couple of different ways that we can do it. I actually like to just jot down my expected counts inside the original table. And I'll show you why. But a lot of the homework questions, because I can't figure out how to program that, it'll give you a different table where you enter your expected values. Okay, but it'll look the same, right? Because for each cell here, I'm going to have an expected count. Okay? And so that means I need the totals for all of these. I get 15 plus 4 plus 10 is 29. Oh, I guess that might not. Oh, so close. I had a 29, but I mixed them up. They don't match exactly. So close. 19 plus 3 plus 10 is 32. How can I make these match? I can't. I can't. That's okay. My grand total is still 61. Funny that they are. Guess it's not that weird. Just reverse. You could go back and adjust the total and adjust your counts. Anyways, whatever. For the males and females. Slight oversight, but that's what you get when I'm doing it on the fly. So here I have a total. Here I have a total. Now for this first cell, my expected count for row 1, column 1, you don't have to use the subscripts, is going to be the row total, which is 29, times the column total, which is 34, divided by the grand total, which is 61. So once you do 29 times 34 divided by 61, I get an expected count of 16.164. Let's keep 3 decimal places. It's tempting to round to a whole value, right? Because you're thinking, okay, well, I can't have a fraction of a person, but what we've seen is you can expect a fraction of a person, right? And so, and in fact, usually our expectations are fractions of people, because that's if we observed it many, many, many times over. So we saw 15, we expected 16.164. Okay. And so now I can say, okay, down here, 16.164. Then I can go on and I can do the same for this cell. This would be the expected for row 1, column 2. And again, you don't need those subscripts. I just want to show you that that's all it means. Is going to be the row total, 29, times the column total, divided by 61, the grand total. 29 times 7 divided by 61, and I get to 3 decimal places 3.328. Right, so down here I'm expecting 3.328. I saw 4, but I'm expecting 3.328. Let's look at this expected value. It's not going to be the same as the one above it, right? Because I have 32 females versus 29 males, right? And so I need to take that into account. And so the expected count for row 2, column 2 is 32 times 7 divided by 61. So I would expect 3.672. And I would jot that down here. So from here, you're able to calculate each of these expected counts. Now that's a lot, right? That's a lot of work, but it's tedious. It's not hard, it's just tedious. And so enjoy it. Not hard, just tedious. What else do you need to do? So now you have your expected counts for each cell. Now to calculate your chi-squared, right, you need to take your observed count, I'll keep it here, minus your expected count, square that, and then divide by the expected count for each of these cells. Okay. Now, I'd say a 2x4 table is a little bit rude. That's huge, right? But I think a 2x3 is reasonable. Which would only cut 2 calculations, right? Or 2 of these. So it's not even that bad. So for each, what you can do, if it simplifies things, then I would list the observed and the expected counts just kind of side by side and do your calculations in a column like that, just because it's hard to show your work otherwise. But then what you'll find is that your chi-squared is the sum of your observed minus the expected squared over the expected. Right. And this is for, do this for each cell. So 1, and then 2, then add them up. And that's going to be your test statistic. Now, last day, let's assume we calculate our chi-squared to be 3.217, just making something up. I made it small because just by looking at these expected counts and how far they are from the observed counts, I don't think they're that far away, right? We have to take into account the spread, which is kind of taking the expected value is taking the place of the spread, right? But in general, I don't think that these are terribly far away. And so that's why I picked a small chi-squared. We need to find the degrees of freedom. Step 3 is find the p-value. We need the degrees of freedom. The degrees of freedom from your formula sheet is the number of rows minus 1 times the number of columns minus 1. How many rows do I have? I have 2 rows and I have 4 columns. Two minus 1 is 1, and 4 minus 1 is 3. So I have 3 degrees of freedom. Now that I have my degrees of freedom, let's assume, actually, once you have your degrees of freedom, sorry, I got carried away. You can go to your table, right? This table's on your formula sheet. Same one we were using last day. And I'm just going to paste it in here. Once you have your degrees of freedom, 3 degrees of freedom, that means that we're going to be sticking to this line and ignoring the rest. Then what we find is we try to place our chi-squared somewhere on this line, right? We fall here, right? Somewhere between 0 and 6.25. So we find that our chi-squared calculated is somewhere between 0 and 6.25. Which means our p-value, or the, right, it says upper tail, but that's the p-value. The p-value is somewhere between 0.1 and 1. Right? Or visually, if you prefer, you can say 3 degrees of freedom maybe looks like this. Yeah. And we said, okay, chi-squared starts at 0. And the next check-in point, or the first check-in point, I should say, at 3 degrees of freedom is at 6.25. Now this number line is a chi-squared, 6.25. And we're told from the table that the area in the tail is 0.1 at 6.25. Now we found our chi-squared calculated, and maybe I'll say what it is so I can refer to it, but it's also nice to do. 3.217. Right, 3.217 on this number line would be somewhere here. So our p-value, we don't know much about it, but I can tell you that this area is bigger than 0.1. And that's good enough, right? That's all we really need to know. But at 0, right? At 0, the area to above it is 1, right? So I'm kind of caught between 0.1 and 1. Not very telling, but it means we have a big p-value. So then this is between 0.1 and 1. And of course, Excel or any other software, an online calculator, or even some calculators will do it for you. You can find the actual p-value, right? But knowing that it's bigger than 0.1, okay, I'm not going to reject H0, right? Because that brings me to the critical value approach, right? We've been using the p-value approach, but let's kind of get used to using the critical value approach as well. So, or this is where I was starting to say earlier, or what I was starting to say, assuming an alpha level of 0.05, and that's our default. We can find the critical value, right? At 3 degrees of freedom, the critical value is when I force the alpha level into the tail and I figure out what my chi-squared needs to be bigger than in order to get there. And so then I find that 7.81 is my critical value. And that's when I have 0.05 in the tail. So my chi-squared critical, which is why I was putting a little calculated here, right? Calculated versus critical. Annoying because C wouldn't work. Right, calculated critical. But our critical value would be 7.81. Which means, right, if we flip it, which means our calculated chi-squared would need to be larger than 7.81 in order for us to reject H0, right? Our conclusion stays the same. We have a large p-value and our chi-squared is not bigger than our critical value, right? So depending on how you want to do your conclusion, or how you're asked to do your conclusion rather, right, that'll determine how you state your conclusion. For chi-squareds, I need you to be able to do both, right? Not at the same time. I'll only ask you, okay, using the critical value, state your conclusion, right? Or using the p-value, state your conclusion. Step 4 is your conclusion. Nice. Using the p-value, which is what we're used to doing, right? So if you're using the p-value, then the argument is, okay, well, my p-value is not less than the alpha level, right? So I do not have enough evidence to reject H0, right? Which means that gender and how a person takes their coffee are independent of each other, right? Because I don't have enough evidence to reject this. Yeah? So let's state that. Since our p-value is between, I guess I only have a range, is between 0.1 and 1. It is not less than the alpha level of 0.05. Now it's really important that you showcase that you know what the p-value is and you say what the alpha level is that you're comparing it to, right? And so I will say this, on test 2, I'm gonna mark it pretty hard, okay? Because I can't mark hard on the final exam because there's no more lessons to learn, right? I'll be way more generous on the final exam, I promise. But I do find it's the only way to correct bad behavior, okay? Is to mark you hard on the test. Oh my gosh, she hates me. No, that's not true. You can do better. I know. I'm like a strict mom. You can do better. I know you can. Okay? So you've been warned, I'm gonna mark hard, but that's only so that you learn for the final exam. And then it's gonna be so easy for me to mark because everyone's gonna get it right. Right? Okay. What was I saying? Oh yeah. So you want to highlight all the things that you've already established, all these things. You're not really coming up with anything new. You're just composing it into a nice, clean conclusion. Right? So you've already done this work. You may as well show it off. So since our p-value is between 0.1 and 1, it is not less than the alpha level of 0.05. which means we do not have enough evidence to reject H naught. Therefore, and I'm just going to copy it because I'm lazy. Gender and how a person takes their coffee are independent of each other. There, not sure that saved any time. I'm gonna give myself just one more line. Can I snag another line somewhere? No, I cannot. I want to keep it all on this page, but using the critical value since our calculated chi-squared of 3.217 is not less, or sorry, is not greater than the critical value of 7.81, we do not have enough evidence to reject H naught. Guess I could go into the next slide, etc. Right, then it's the same. This should say H naught. Your conclusion has to be about H naught. If you never mention HA, that's fine by me, right? Usually, if you have enough evidence to reject H naught, then you say, okay, in favor of HA, right? But I don't want to see any conclusions in terms of the alternative. Why? Because we did all our testing assuming that the null hypothesis was true until we found evidence against it. In this case, we didn't. And so then we just kind of stick with H naught. Nice. Okay. So this was a made up chi-squared, and maybe I'll spend some time calculating it, but we've got one where it's calculated for us. So let's use that instead. Any questions before we do another example? Okay, yeah.
When you were talking about unit expected values of 5 or more.
Oh, yeah.
For this one, it was just because we made it up.
Yeah.
Yeah. So if we saw something like this, we'd be like, we can't do it.
Yeah. Okay. Or you could still do it, but you would say your results are unreliable.
Okay.
But that's beyond us, beyond this course.
So we didn't.
But yeah, this would be bad.
Okay. You don't have to prove any of that for this, for the chi-squared one.
No. No. No, I can't remember if I make you check it. I'll get back to you, but on the test, the expected counts will be greater than 5, right? And for any chi-squared, you need independence, and in this case, we extend it to independence between these categories, but also independence within the genders, right? So no overlap, and then expected counts greater than 5, and those are our only conditions for a chi-squared, and I totally forgot to say it anywhere here. But I'm sure Mina didn't forget in this example. Any other questions before we do this one though? Okay. So Students in grades 4 to 6 were asked whether good grades, athletic ability, or popularity was most important to them. A two-way table separating the students by grade and by choice of most important factors shown below. So right away, if you see something like this on the test, right, then you know it's going to be a chi-squared test of independence, right? And so just seeing this tells you, okay, right, that should flag to you, right? And do these data provide evidence? That's a hypothesis test. And this tells me it's a chi-squared test of independence. And then we can confirm that by rereading it, right? Do these data provide evidence to suggest that goals vary by grade, right? Which we could rephrase as the grade that a student is in is independent of what their overall goal is, right? Or the goals are independent of the grades. Right? Okay, so you can visualize it, but I don't really make you do that. I just make you work with the table. Our hypotheses, our null hypothesis is that grade and goals are independent. So on our formula sheet, we have a generic statement of the variables are independent, but just like the other chi-squared, I need you to reformulate that as something question specific, right? Grades and goals are independent, right? Telling me that you understand what the variables are, right? The observed distribution of what equals the expected distribution, which is what, right? That kind of thing. And so I'll be looking out for that. Our alternative is that grade and goals are dependent or not independent if you prefer, right? Goals do vary by grade. So we've seen it, and sometimes to summarize a chi-squared, we put the little degrees of freedom down in the subscript. I don't make you do that, but just so that you're aware of what that means, it just says chi-squared at this degrees of freedom, right? Because that determines the shape. So the test statistic is calculated like this: observed minus the expected squared over the expected, add them all up. And we've already seen the degrees of freedom. R is the number of rows, and C is the number of columns. I spell it out on the formula sheets, but if you prefer R minus 1 times C minus 1, that's fine. K is the number of cells. We used K for the chi-squared goodness of fit, right? For the number of categories. And now K has turned into the number of cells, but we calculate our degrees of freedom differently anyways, so it doesn't matter. And so we calculate the degrees of freedom differently for one-way and two-way tables. This was for the goodness of fit test. We had degrees of freedom is K minus 1, the number of categories minus 1. And for two-way tables, we're testing independence. And the degrees of freedom is R minus 1 times C minus 1. And as we've seen, the p-value is the area under the chi-squared at some degrees of freedom curve above the test statistic. So here, a summary of how to calculate these expected counts. The expected count for this orange cell, right? We observed 63. But we expect 119 times 247 divided by 478. So we expect 61, which is more on par with the numbers that we would be expecting. Kind of larger, non-issue ones. I should have just put zeros on all those numbers earlier. Well, we wouldn't have a problem. For the green cell, right? Row total 119 times the column total 141 divided by the grand total 478. And then you would keep going and find these expected counts for all of these. What's the expected count for this cell, this middle cell? I would expect E22, right? Row 2, column 2 is 119 times 141 divided by 478. Thank you. I would have fallen for the decoy too. Rude. Thank you. 176 times 141 divided by 478. I would expect roughly 51.916. But I guess it just wants the numbers. Is it the first one? Yeah. She's rounded, but I will say this. This value is rounded, but I want you to keep at least 2 decimal places. Especially for those online assignments, I think it'll tell you what to round to. And of course, it'll mark it wrong if you're using the wrong rounding. And so, but I also want you to be comfortable with, okay, I'm expecting this many. It doesn't have to be 52. It can be 51.916 or 51.92, but just follow the rounding instructions. Usually on the test, I try to be nice and I make sure that all the expected counts do just go to like 2 decimal places or something like that. And so I try to be nice, and then you have to keep all your decimal places. So just like we did earlier, right, we can calculate all the expected counts for each of the cells, right? And so the expected counts are shown in blue next to the observed counts. So I saw 63, I was expecting 61, not that far off, right? But do any of these look kind of far off? Maybe the 88 and 91, close, but we'll see. So once you do 63 minus 61 squared divided by the expected count, 61, plus 31 minus 35 squared over 35, blah, 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 blah. Shouldn't even type them all out. We get a calculated chi-squared, a real one finally, of 1.3121. Our degrees of freedom, we have 3 rows. R is 3, and we have 3 columns. So C is 3. 3 minus 1 times 3 minus 1 is 2 times 2, which is 4 degrees of freedom. Now, one problem that I have with my mini version of the chi-squared table is I capped it at 5 degrees of freedom. Which means what? The largest table that I could possibly give you, right, could be, I don't know, 3 by 3, 4 by, can I give you 4 by 3? 3 times 2, no, I can't. Can give you 4 by 2. That's probably as big as it's gonna get, right? I guess I could do 5 by 2 still. 6 by 2, fun. No thanks. But it also means for the goodness of fit test, right, where we have the number of categories -1, I'm limited to 6 categories, which is kind of limiting and kind of an oversight, because usually a lot of this data is over days, right? And there's 7 days a week. And so then I can't do those. We could ignore the weekends. Then we can do it. Okay. So she's got a bigger chi-squared table that she's using, right? But that's okay. For us, I guess I needed this thing. We've got 4 degrees of freedom, so I'm gonna only stick to this row. And I try to place my 1.3121. We find that our chi-squared of 1.3121 is caught between, so zeros at the end here, right? 0 and 7.78. Which means my p-value is between, again, 0.1 and 1, right? At 0, the area in the tail is 1. So 0.1 and 1. Can ignore this. This uses a bigger table. So for us, we've got these itty bitty chi-squareds, boring. So if our p-value is large, which it is, right, somewhere between 0.1 and 1, that's large. So then we do not have enough evidence to reject H naught. So here she's kind of sloppy. I would take marks off. No, well, maybe. Keep guessing. And I haven't decided. Since the p-value is large, although I feel like I've said it enough, right, is not less than the alpha level of 0.05, then we don't have enough evidence to reject H naught, or sometimes we just say we fail to reject H naught. The data do not provide convincing evidence that grades and goals are dependent, right? And so it doesn't appear that goals vary by grade. Nice. Recall the mini-ag data from last day that we collected, right? We found that it was definitely not evenly distributed, right? But now, what if I wanted to change this into a chi-squared test of independence? what would you need to do? You would need to have some new category, right, that you want to compare across. And I think the best one I can come up with is these were bought in Canada. But what about if I did the same thing in the States, right? I bought some mini eggs in the States and I found some counts. And then because I'm pretty sure mini eggs are extremely American in the sense that I don't think they have mini eggs in Europe, for example. Let's say they have them in Mexico as well. Question?
Just random question. Mini eggs are Cadbury, right?
Oh, so maybe in the UK then.
Yeah, I was thinking like.
Okay, well, it's gonna melt in Mexico, let's say the UK. Although then can I, instead of the UK, can I say Britain just so I don't have two U's? Thank you. Oh, wouldn't it be so cute if I had a Argentina instead of the US? Because then it would be ABC. Oh, you're cut. Argentina. Whether that makes sense or not, because then I can have C, A, and B. ABC. Australia, maybe. No, well, I guess it might melt in Argentina too. Okay, I'll go for the colonies. Australia. There. That's more fun. I'll need someone to fund my research. I'll go to Australia and I'll go to Britain and I'll do the same tests again. And then I'll have real data. The school's like, not the time for that. But also you can just call someone there. That's true. Boring. All right. Let's pretend we did the same thing in Australia. What numbers? Let's make let's kind of push the limits, right? So what do I mean by pushing the limits? I want to see how far from these counts, right? If the country is independent of the colors, right? Or the colors are independent of the country is usually how we would phrase it, right? Then I would expect kind of a similar distribution, not too far off, but similar in Australia, but also in Britain, similar to what we saw in Canada. Right? And so then, but I want to push the boundaries a little bit because I want to get kind of a bigger chi-squared so that we can reject H naught. And so now, maybe what I'll do is I'll phrase the question here. Is there evidence, right? Whenever you see is there evidence, it's a full hypothesis test. Is there evidence that the distribution, or I'll just make it simple, that the color of mini eggs is dependent on the country where we purchase them? This makes it look like I was, I'll make it there. make up some numbers. Let's see here. We've got, let's go for 10, 32, 15, I don't know, 27. Why not? Which means I sampled 10 plus 32 plus 15 plus 27. So 84 in Australia. I went all that way and I only sampled 84 mini eggs. Oh well. Then I thought better of it. And in Britain, I sampled 74 in Britain. What? I know. Really living large here. And let's see here. And then I did 150 yellow. I have no idea where this is going. 164 and 121.
I am a student here. Where are you a student over there? No. Not going over there.
It's really for that.
Well, I'm like, should we call security? Is this like a brawl? Was that security?
I don't think security would speak.
I actually had to contact security recently because I was sitting in the S building and there was this group of high schoolers and one of them was saying something about a type of gun and I'm like, excuse me? So I look up and one of them pulls out a bomb shaped like a gun, but then he starts pointing it around like it's an actual gun and I'm like,
That's not, yeah, it's like, no, we don't,
"There's so
no,
much going on."
it's like we can't
It's
be
so
doing
bad.
that. Yeah,
So bad.
yikes. Okay, well, at least we can go back to our calculations.
So nice.
We look and see, or they.
I'll go.
They probably went to the trade building.
They went outside and now they're fighting.
Oh, yeah.
Yeah, there's no one out there.
Crazy. The trade building sometimes gets groups of guys sitting there a lot and people are either really quiet or really loud.
It's a nice place to sit though.
Yes, the trades building is so.
Right?
Oh, there's a freaking plane.
Yeah. Mm-hmm.
Vending machine. That's so fun. Invisible double take when someone walks by and they're like, wait a minute, that's computer chips, sandwiches, and sometimes cookies.
For a total of 91 pink mini eggs. And then I can find the totals across each of these, 20 and 32 and 150. I hope I don't regret going a little wild in Britain there. 22 plus 15 plus 164. I just go where the data tells me. 38 plus 27 plus 121. My only concern is that it's going to maybe make my expected counts weird, but I would expect large counts out of a sample of 509. Right? And I get a total of 91 plus 202 plus 201 plus 186. Wow. That, I mean, everything's coming up Emily today. 87 plus, I gotta confirm, 680, wow. I didn't even plan that. Just going rogue up here. Okay, now, of course, Excel, you can enter just this table. It doesn't even need the totals. And what it'll do is it'll calculate the chi-squared in the background and it'll just spit out the p-value. saving you a ton of work, right? Even calculating the expected counts in Excel is going to be a lot easier than doing it by hand, but here we are. We're stuck doing this calculation. Beside each of these, I'm going to write my expected count. 91 times 87 divided by 680. Let's do 11.64. And if I forget to check the conditions this time, remind me, but we do need the expected counts to check the conditions. So, but I might forget. So let's keep 2 decimal places for the expected counts. And so I'll go through and do these 91 times 84 divided by 680. 11.24. 91 times 509 divided by 680. 68.12. Technically, these expected counts should add to 91, but because we're rounding, right, as long as you're kind of close, right, with the rounding taken into account, then you can check it that way, but I'm going to keep going. Hopefully I didn't do it weird. So slow. I probably should have only done 2 countries, but that's okay. And another reason, but I was so excited about ABC, is now I'm gonna have 6 degrees of freedom. But that's okay. I'll dig up the big table. We can do it or Google it. 201 times 84. Back to the grind. Well, this one's quite far off. 15 versus 24.83. I guess all my calculations assume I did it right and I didn't slip up, not even once. Feels unlikely. Now my chi-squared is the sum of the observed minus the expected squared over the expected, which is going to look like seven minus 11.64. I don't want to do this. 11.64 plus 10 minus 11.24 squared divided by 11.24. And now I bust out the big guns. It's a random sheet. Okay. instead of putting in the table, if I gave it a table, I would be able to get the chi-squared value. Okay. Good. This is going to be my observed. And this is going to be my expected. I'm going to jot them down 7. Doesn't really matter which order. 10, 74.
20,
Thank you.
22. 150. Are we going across? Yeah.
Yeah.
22, 15,
Nice.
164,
Wow.
38, 27, and 121.
Nice. Oh, these expected counts. Okay, we can do it.
I can read them out. 11.64, 11.24, 68.12, 25.84, 24.95, 151.20, 25.74, 24.83, 150.41,
Oops.
23.80, 22.98, and 139.23.
Thank you.
I know I hate having to go back and forth.
It is annoying. Okay, now for each of these, let's see if I can pull this off. I want to do in brackets the observed minus the expected, close the brackets, and square it. What do I, to the power of, there it is, to the power of 2. Hard to do on my iPad, I guess. I'll throw some kind of precautionary brackets around there just because I don't want to divide my power divided by the expected count. I want to make sure that it's all divided by the expected count divided by the expected count.
Nice.
And now, will it do it? Ah. I want to send that down. Aha. I assume it did it. So our chi-squared is going to be the sum of all of these. Hey. My iPad is great for a lot of things. Whoa. But definitely not this. Did we do it? Amazing. While we're here, oops, equals chi-squared dot dist right tail. That sounds reasonable. Let's check it out. Returns the right-tailed probability, which is what we want, of the chi-squared distribution. Score. I don't know why they have the chi-squared dot dist. I think just for symmetry, but it gives the area to the left, which is probably never what you want. But you always want the right tail. And so let's use the chi-squared dist dot right tail, and it wants this guy. And our degrees of freedom, we said were 6, right? 4 minus 1 is 3 times 3 minus 1, which is 2. So 3 times 2 is 6. While we're here, right? Score. Now, I'm going to screenshot this. Might be loud or make no noise at all. I never know. Wait. We did it. Nope, all the way. I can't believe it. We made it. And it was only, I don't know if that was less painful than just doing it by hand, but it was more fun for me. So we found our chi-squared was 23.04083. And this was using our chi-squared dot, or maybe it's one word, I can't remember. Chi-squared dot dist dot right tail of 23.04083 and 6 degrees of freedom. So you could do it like this, right? Or you can try feeding it into just the table and using the chi-squared, I can't remember what it's called, but can poke around. This is our p-value. That's nice. Hard to find a critical value, so let's just stick to the p-value. But I'll also jot down the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. We had 4 rows and 3 columns. Way too much work. 3 times 2 is 6.
So when we, finding the degree of freedoms, we don't include the total row, right? We just
No,
do
just the number of categories.
Okay.
Yeah, totally. Haha, pun intended, I guess. Okay, so this, our p-value is 0.000783, right, from software. Better, way better than the table. Oh, I guess should label the steps. Step 3, find the p-value. Using Excel. Your conclusion then is, since our p-value of 0.000783, right, show it off, is less than our alpha level, alpha equal to 0.05, we have enough evidence to reject H naught in favor of HA. clarify that this is H naught in favor of HA. Therefore, what was our null hypothesis and our alternative hypothesis? I got carried away. But I forgot to state our null and alternative hypotheses, and I forgot to check the conditions. Oh boy. We can check our conditions. Mini eggs bought in Canada, Australia, and Britain, we can assume are independent of each other. But also we assume that the one mini egg can only be classified as one of these colors. So they're independent. But also, I have all my expected counts are greater than 5. And so the chi-squared test applies. I'll write that down. But I wanted to do the conclusion. Is there evidence that the color of mini eggs is dependent on the country where we purchase them? Yes, there is. Right, we had to assume that they were independent until we found evidence against that. Uh-oh. Therefore, I've got a decision to make here, don't I? Do it properly for posterity? I think so. I'll clean this up here. So our null hypothesis is that the color and country purchased are independent. Kind of a shorthand version. State the hypotheses. At least we've done the hardest part, calculating the chi-square. The color and country purchased are not independent. Then I can bring in our counts and our expected counts. Step 0, check the conditions. We need the expected counts. That's why it's coming. I'm slipping it in here. The conditions for a chi-squared are independence. Yes. I don't think I even finished it. I abandoned it. We assume the colors are independent. Right, one egg can only be one color. And country purchased are independent. Right, there's no reason to think that a mini egg that you counted in Canada has suddenly popped up in a bag in the UK, right? And so that's why we say that they're independent.
You want us to write that for the test?
Just that they're independent. Yeah. Independent of each other and independent within the categories. Which we could also phrase as the categories are all disjoint. Right. All categories are disjoint. And then the sample size condition or I guess I don't call it a condition. It is a sample size condition. But we need at least 5 expected counts in each cell. Right, we see that each cell has, what's our smallest one? At least 11, right? And so it's satisfied. Has at least 11 expected. So it checks out. Then we're ready for step 2, which we already did. Calculate the test statistic. That's what we did here. Uh-oh. Like nothing happened. Oh, except I need to move this over. It's lost forever off the page. But what's nice is now I have room to do my conclusion. So our p-value, which we found just using Excel, is less than 0.05. We have enough evidence to reject H0 in favor of HA. Therefore, if we have enough evidence to reject H0, then we can say that the color and country purchased are not independent of each other, right? The country where you purchased your mini eggs, right, will determine, right, what a reasonable distribution for the colors is. Or is there evidence that the color of mini eggs is dependent on the country where you purchase them? There is evidence that the color of mini eggs is dependent on the country where we purchase them. Yikes. No conclusion for us. Just have hair in my throat or something. Therefore, uh-oh. I'm just gonna steal this here. Whichever one you want to choose. If you want to choose the alternative and just use that in your conclusion, that's fine. But I'll just steal from the question itself. Evidence that the color of mini eggs is dependent on the country, but we purchase them, period. Hey, you guys didn't stop me.
It's okay.
So sorry.
We were invested.
There, if you have any questions, let me know. Otherwise, big day on Friday. We introduce numerical data. We start with means, kind of a big deal. Pretty fun. All right, if you have any questions, let me know. Otherwise, see you.